Okay, welcome to Season 1, Episode 1 of Learning in Public. And this season features this very famous book, Structure and Interpretation of Computer Programs, um, which is a computer science textbook by the Massachusetts Institute of Technology. Um, it has been written by three professors, Harold Abelson, Gerald J. Sussman, and with Julie Sussman. And it is known, according to Wikipedia, as the wizard book in the hacker culture, and it teaches fundamental principles of computer programming, including recursion, abstraction, modularity, and programming language design and implementation. The first edition has been published in 1984, and the second edition instead in 1996. And it has been used as the textbook for the MIT introductory course in computer science from the date of the first publication to 2007. This book focuses on discovering general patterns for solving specific problems and building software systems that make use of those patterns. So let's get the PDF. Let's get the PDF and let's start. Okay. Where is my PDF? Okay, first chapter. Let's see how long I can go. I've skimmed through the first pages of the book. I've seen that after 20 pages or so, there are some exercises. The plan is to stop right before the exercises, and maybe the next video will be focused on these exercises. So let's start. Building abstractions with procedures. So this chapter opens with this citation from an essay concerning human understanding by John Locke, who said, the acts of the mind wherein it exerts its power over simple ideas are chiefly these three. So let's see if I can take a lighter. Okay, combining several simple ideas into one compound one, and thus all complex ideas are made. Okay? The second one is bringing two ideas, whether simple or complex, together and setting them by one another so as to take a view of them at once without uniting them into one, by which it gets all its ideas of relations. Okay, and the third is separating them from all other ideas that accompany them in their real existence, and this is called abstraction, and thus all its general ideas are made. So okay, three main points here by John Locke. First, combine simple ideas into a compound one, then bring two ideas together and understand the relationship that intercourse between the two ideas. And the third is the ability to separate an idea from all the others in their real existence, and this is called abstraction. Okay. I see the point. Okay. We are about to study the idea of computational process. Computational processes are abstract beings that inhabit computers. This is a very strange incipit for a computer science textbook. I'm starting to understand why the book is so popular and also probably why it is called the wizard book. As they evolve, processes manipulate other abstract things called data, yes. And the evolution of a process is directed by a pattern of rules called a program. People create programs to direct processes. In effect, we conjure the spirits of the computer with our spells. Esoteric flavor. A computational process is indeed much like a sorcerer's idea of a spirit. It cannot be seen or touched. It is not composed of matter at all. Okay, I don't like this stuff. I don't know why, but I really don't. I'm gonna skip this. Sorcerer spells, okay. They are carefully composed from symbolic expressions in arcane and esoteric programming languages that prescribe the tasks that we want our processes to perform. Okay. Like the sorcerers, again with this sorcerer, come on. Even small errors, usually called bugs or glitches in programs, can have complex and unanticipated consequences. Real-world programming, however, requires care, expertise, and wisdom. Yeah. Master software engineers have the ability to organize programs so that they can be reasonably sure that the resulting processes will perform the tasks intended. They should know how to structure programs so that unanticipated problems do not lead to catastrophic consequences. And when problems do arise, they can debug their programs. Okay. Programming in Lisp. We need an appropriate language for describing processes, and we will use for this purpose the programming language Lisp. Okay, so we are gonna learn Lisp. Cool. It should be a functional programming language. The only functional programming language that I know, I know very little, is Haskell. Just as our everyday thoughts are usually expressed in our natural language, English, French, or Japanese, and descriptions of quantitative phenomena are expressed with mathematical notations, our procedural thoughts will be expressed in Lisp. Okay? Lisp is a programming language from the late 50s. The language was conceived by John McCarthy. Oh, I didn't know that. And is based on his paper Recursive Functions of Symbolic Expressions and Their Computation by Machine. Wow. Lisp is a practical programming language. A Lisp interpreter is a machine that carries out processes described in the Lisp language. Okay. Lisp is an acronym for list processing. Okay. History of Lisp. Okay, thus Lisp is by now a family of dialects which, while sharing most of the original features, may differ from one another in significant ways. The dialect of Lisp used in this book is called Scheme. So we are going to learn how to code in Scheme. Nice. Because of its experimental character and its emphasis on symbol manipulation, Lisp was at first very inefficient for numerical computations, at least in comparison with Fortran. Yeah, Fortran is very fast. Over the years, however, Lisp compilers have been developed that translate programs into machine code that can perform numerical computations reasonably efficiently. Okay. Lisp has not yet overcome its old reputation as hopelessly inefficient, but today is used in many applications where efficiency is not the central concern. For example, Lisp has become a language of choice for operating system shell languages and for extensions languages for editors and CAD systems. So if Lisp is not a mainstream language, why are we using it as the framework for our discussion of programming? Because the language possesses unique features that make it an excellent medium for studying important programming constructs and data structures and for relating them to the linguistic features that support them. The most significant of these features is the fact that Lisp descriptions of processes, called procedures, can themselves be represented and manipulated as Lisp data. Okay. The ability to blur the traditional distinction between passive data and active processes. Okay, we will see. We will see these unique features. Above and beyond these considerations, programming in Lisp is a great fun. Yeah. We will see. Okay, the elements of programming. Oh, this is so nice. A powerful programming language is more than just a means for instructing a computer to perform tasks. The language also serves as a framework within which we organize our ideas about processes. This is very powerful. Thus, when we describe a language, we should pay particular attention to the means that language provides for combining simple ideas to form more complex ideas. And every powerful language has three mechanisms for accomplishing this. Primitive expressions, representing the simple entities the language is concerned with. Means of combination, by which compound elements are built from simpler ones, and means of abstractions, by which compound elements can be named and manipulated as units. Yeah, this is partially aligned with the initial citation from John Locke. In programming, we deal with two kinds of elements, procedures and data. And later we will discover that they are really not so distinct. Informally, data is stuff that we want to manipulate, and procedures are descriptions of the rules for manipulating the data. In this chapter, we will deal only with simple numerical data, which as pointed out by the footnote, numerical data is not simple at all. Okay, but I see the point. So that we can focus on the rules for building procedures. In later chapters, we will see that the same rules allow us to build procedures to manipulate compound data as well. Okay, expressions. One easy way to get started at programming is to examine some typical interactions with an interpreter for the scheme dialect of Lisp. Imagine that you are sitting at a computer terminal, you type an expression, and the interpreter responds by displaying the results of its evaluating that expression. One kind of primitive expression you might type is a number. So if you present Lisp with a number 486, the interpreter will respond by printing 486. Okay? I'm not going to show you the terminal interacting with the Lisp interpreter, maybe in the next episodes. Expressions representing numbers may be combined with an expression representing a primitive procedure, such as plus or times, multiply, to form a compound expression that represents the application of the procedure to those numbers. So for example, plus 136, 37, and 349. This is an addition. The result is 486. Okay. Other examples with minus, with subtraction, multiplication, and division. Okay. Also with float numbers and integers. Expressions such as these, formed by delimiting a list of expressions within parentheses in order to denote procedure application, are called combinations. So these expressions, formed by delimiting a list of expressions within parentheses in order to denote procedure application, are called combinations. The leftmost element is called the operator, and the other elements are called operands. So in this case, the operator is plus, and the operands are 2.7 and 10. The value of a combination is obtained by applying the procedure specified by the operator to the arguments that are the values of the operands. And this is known as prefix notation. It is somewhat confusing at first because it departs significantly from the customary mathematical convention, in which if you want to do the sum of 2.7 and 10, you write 2.7 plus 10 and not plus 2.7 and 10. But the prefix notation has several advantages, and one of them is that it can accommodate procedures that may take an arbitrary number of arguments. So for example, plus 21, 35, 12, 7, or multiplication of 25, 4, and 12. Non-ambiguity can arise because the operator is always the leftmost element and the entire combination is delimited by the parentheses. A second advantage, so the first advantage is that you can use an arbitrary number of arguments, and the other one is that it extends in a straightforward way to allow combinations to be nested. That is, to have combinations whose elements are themselves combinations. And this is an example. So in this case, the interpreter does at first the multiplication between 3 and 5, which is 15, and then does the subtraction between 10 and 6, which is 4, and then sums 15 and 4 to obtain 19. There is no limit in principle to the depth of such nesting and the overall complexity of those expressions. Okay, this is very confusing for humans, but we can use a formatting convention known as pretty printing, so that basically a long combination is written so that the operands are aligned vertically. And so you look at the indentations to understand the structure and the order of the expressions. Okay. This is how the interpreter works. It reads an expression from the terminal, evaluates the expression, and prints the result. This is the popular read eval print loop, REPL. Okay, naming and the environment. A critical aspect of a programming language is the means it provides for using names to refer to computational objects. We say that the name identifies a variable whose value is the object. In the scheme dialect of Lisp, we name things with define. So for example, define size2 causes the interpreter to associate the value 2 with the name size. Once the name size has been associated with the number 2, we can refer to the value 2 by name. So if you type size in the terminal, in the interpreter, you get 2. Further examples, so you can define pi, you can define radius, and you can compute the circumference. Define is our language simplest means of abstraction, for it allows us to use simple names to refer to the results of compound operations, such as the circumference computed above. Yeah, yes, because in general, computational objects may have very complex structures, and it would be extremely inconvenient to have to remember and repeat their details each time we want to use them. And indeed, complex programs are constructed by building step by step computational objects of increasing complexity. It should be clear that the possibility of associating values with symbols and later retrieving them means that the interpreter must maintain some sort of memory that keeps track of the name-object pairs. This memory is called the environment, or more precisely, the global environment. Evaluating combinations, one of our goals in this chapter is to isolate issues about thinking procedurally. As a case in point, let us consider that in evaluating combinations, the interpreter is itself following a procedure. To evaluate a combination, do the following. Evaluate the subexpressions of the combination, okay? Apply the procedure that is the value of the leftmost subexpression, the operator, to to the arguments that are the values of the other sub-expressions, the operands. Okay, I see. And even this simple rule illustrates some important points about processes in general. Because observe that the first step dictates that in order to accomplish the evaluation process for a combination, we must first perform the evaluation process on each element of the combination. Okay? Thus, the evaluation rule is recursive in nature. That is, it includes as one of its steps the need to invoke the rule itself. I think I've understood, but I want to read this passage once again. This simple rule illustrates some important points about processes in general. Observe that the first step, so evaluate the subexpressions of the combination, dictates that in order to accomplish the evaluation process for a combination, we must first perform the evaluation process on each element of the combination. Yes. Thus, the evaluation rule is recursive in nature. Okay, I see, I've understood. That is, it includes as one of its steps the need to invoke the rule itself. Notice how succinctly the idea of recursion can be used to express what, in the case of a deeply nested combination, would otherwise be viewed as a rather complicated process. For example, evaluating these three representations of a combination requires that the evaluation rule be applied to 4 different combinations. Viewing evaluation in terms of a tree, we can imagine that the values of the operands percolate upward, starting from the terminal nodes and then combining at higher and higher levels. In general, we shall see that recursion is a very powerful technique for dealing with hierarchical tree-like objects. In fact, the percolate values upward form of the evaluation rule is an example of a general kind of process known as tree accumulation. Yeah, I didn't know this term. I didn't know this, neither the term nor the concept of tree accumulation. I will look into that right after this video. Next, observe that the repeated application of the first step brings us to the point where we need to evaluate not combinations, but primitive expressions such as numerals, built-in operators, or other names. And we take care of the primitive cases by stipulating that the values of numerals are the numbers that they name. The values of built-in operators are the machine instruction sequences that carry out the corresponding operations, and the values of other names are the objects associated with those names in the environment. Okay. As we shall see in chapter 3, the general notion of the environment as providing a context in which evaluation takes place will play an important role in our understanding of program execution. Notice that the evaluation rule given above does not handle definitions. For instance, evaluating define x3 does not apply define to two arguments, one of which is the value of the symbol x and the other of which is 3, since the purpose of the define is precisely to associate x with a value. That is, define x3 is not a combination. Such exceptions to the general evaluation rule are called special forms. Define is the only example of a special form that we have seen so far, but we will meet others shortly. And each special form has its own evaluation rule. Compound procedures. We have identified in Lisp some of the elements that must appear in any powerful programming language. Numbers and arithmetic operations are primitive data and procedures. Nesting of combinations provides a mean of combining operations. And definitions that associate names with values provide a limited means of abstraction. Now we will learn about procedure definitions, a much more powerful abstraction technique by which a compound operation can be given a name and then referred to as a unit. Okay. We begin by examining how to express the idea of squaring. We might say to square something, multiply it by itself. This is expressed in our language as define square x. Okay. We can understand this in the following way: to square something, multiply it by itself. So we have here a compound procedure which has been given the name square. The procedure represents the operation of multiplying something by itself. The general form of a procedure definition is define name, formal parameters inside parentheses, and then the body of the definition. So basically, the name is a symbol to be associated with the procedure definition in the environment. The formal parameters are the names used within the body of the procedure to refer to the corresponding arguments of the procedure, and the body is an expression that will yield the value of the procedure application when the formal parameters are replaced by the actual arguments to which the procedure is applied. Okay, this is very clear. This is very clear. Okay, of course, having defined square, we can apply to a numeral like 21 or to an expression like plus 205, or we can apply to an expression using square. So square 3 is square of square 3, so 81. And we can also use square as a building block in defining other procedures. So for example, we can define sum of squares using the square defined above. Compound procedures are used in exactly the same way as primitive procedures. Indeed, one could not tell by looking at the definition of sum of squares given above whether square was built into the interpreter like plus or star, or defined as a compound procedure. The substitution model for procedure application. To evaluate a combination whose operator names a compound procedure, the interpreter follows much the same process as for combination whose operators name primitive procedures, which we described in section 1.1.3. That is, the interpreter evaluates the elements of the combination and applies the procedure, which is the value of the operator of the combination, to the arguments, which are the values of the operands of the combination. We can assume that the mechanism for applying primitive procedures to arguments is built into the interpreter. For compound procedures, the application process is as follows. To apply a compound procedure to arguments, evaluate the body of the procedure with each formal parameter replaced by the corresponding argument. To illustrate this process, let's evaluate the combination F5, where F is the procedure defined before. We begin by retrieving the body of F, which is the application of sum of squares to two expressions, plus A1 and times A2. Then we replace the formal parameter A by the argument 5. And so we have the sum of square of the two expressions plus 5(1) and times 5(2). And so the problem reduces to the evaluation of a combination with two operands and an operator sum of squares. So basically, evaluating this combination involves three subproblems. Yeah, this is very clear, okay. The process we have just described is called the substitution model for procedure application. It can be taken as a model that determines the meaning of a procedure application, insofar as the procedures in this chapter are concerned. However, there are 2 points that should be stressed. The purpose of the substitution is to help us think about procedure application, not to provide a description of how the interpreter really works. Typical interpreters do not evaluate procedure applications by manipulating the text of a procedure to substitute values for the formal parameters. In practice, the substitution is accomplished by using a local environment for the formal parameters. We will discuss this more fully in Chapter 3 and Chapter 4 when we examine the implementation of an interpreter in detail. I want to read it again. The purpose of the substitution is to help us think about procedure application, not to provide a description of how the interpreter really works. Okay, so it's really straightforward to reason in terms of substitution, but apparently the interpreters, or at least the Lisp interpreter, works differently, and we will discover how the Lisp interpreter works in Chapter 3 and 4. And over the course of this book, we will present a sequence of increasingly elaborate models of how interpreters work, culminating with the complete implementation of an interpreter and compiler in Chapter 5. Wow, this is so cool. So we are going to build a compiler and an interpreter. This is great. The substitution model is only the first of these models, a way to get started thinking formally about the evaluation process. Okay. In general, when modeling phenomena in science and engineering, we begin with simplified, incomplete models. True. As we examine things in greater detail, these simple models become inadequate and must be replaced by more refined models. The substitution model is no exception. In particular, when we address in chapter 3 the use of procedures with mutable data, we will see that the substitution model breaks down and must be replaced by a more complicated model of procedure application. Okay, we will see in chapter 3. Applicative order versus normal order. According to the description of evaluation given before, the interpreter first evaluates the operator and operands and then applies the resulting procedure to the resulting arguments. Okay? This is not the only way to perform evaluation. An alternative evaluation model would not evaluate the operands until their values were needed. Is this a sort of lazy computation? An alternative evaluation model would not evaluate the operands until their values were needed. I think this is the definition of lazy computation. Instead, it would first substitute operand expressions for parameters until it obtained an expression involving only primitive operators, and would then perform the evaluation. If we use this method, the evaluation of F5 would proceed according to the sequence of expansions, followed by the reductions. I'm not sure this is the definition of lazy computation. I don't know. This gives the same answer as our previous evaluation model, of course, but the process is different. In particular, the evaluations of plus 5.1 and multiply 5.2 are each performed twice here, corresponding to the reduction of the expression multiply xx with x replaced respectively by plus 5.1 and multiply 5.2. This alternative fully expand and then reduce evaluation method is known as normal order evaluation, in contrast to the evaluate arguments and then apply method that the interpreter actually uses, which is called applicative order evaluation. See exercise 1.5, where normal order and applicative order evaluation do not give the same result. Okay, we will see. Lisp uses applicative order evaluation partly because of the additional efficiency obtained from avoiding multiple evaluation of expressions such as those illustrated with plus 5.1 and multiply 5.2 above, and more significantly because normal order evaluation becomes much more complicated to deal with when we leave the realm of procedures that can be modeled by substitution. On the other hand, normal order evaluation can be extremely valuable tool, and we will investigate some of its implication in chapter 3 and chapter 4. Okay. Conditional expressions and predicates. The expressive power of the class of procedures that we can define at this point is very limited, because we have no way to make tests and to perform different operations depending on the result of a test. For instance, we cannot define a procedure that computes the absolute value of a number by testing whether the number is positive, negative, or zero, and taking different actions in the different cases according to the rule. The rule shown here. This construct is called a case analysis, and there is a special form in Lisp for notating such a case analysis. It's called cond, which stands for conditional, and it is used as follows. Okay. So condition and then the value. So the general form of a conditional expression is condition predicate, yeah, P1 is predicate 1 corresponding to expression 1, predicate 2 corresponding to expression 2. And these are called clauses. The first expression in each pair is a predicate, that is, an expression whose value is interpreted as either true or false. Conditional expressions are evaluated as follows. The predicate P1 is evaluated first. If its value is false, then P2 is evaluated. And so on. This process continues until a predicate is found whose value is true, in which case the interpreter returns the value of the corresponding consequent expression as the value of the conditional expression. If none of the predicates is found to be true, the value of the cond is undefined. The word predicate is used for procedures that return true or false, as well as for expressions that evaluate to true or false. Okay. The absolute value procedure ABS makes use of the primitive predicates greater, lesser, less, and equal. Another way to write the absolute value procedure is define abs of x that is associated with the procedure, the conditional procedure. Which basically can be interpreted if x is less than 0, return minus x, otherwise return x. Yeah, if x is less than 0, return, so for example, if x is minus 2, return minus 2, so plus 2, otherwise return 2. So for example, if x is 2, the conditional procedure returns 2. Else is a special symbol that can be used in place of the predicate in the final clause of a cond. I see. We can also use the special form f. If a restricted type of conditional that can be used when there are precisely two cases in the case analysis. The general form of an if expression is if predicate consequent alternative. Okay, this is very easy. In addition to primitive predicates, there are logical composition operations which enable us to construct compound predicates. The three most frequently used are these: and, or and not. Okay? And or are special forms, not procedures, because the sub-expressions are not necessarily all evaluated. Not is an ordinary procedure. Yeah, I see why. Because let's take and, for example, the interpreter evaluates the expression E one at a time in left to right order. If any E evaluates to false, the value of the and expression is false. So basically, the evaluation stops as soon an expression is false. And the same applies to or. If any e evaluates to a true value, the value is returned as the value of the or expression. Yeah. Okay, we did it. Here we have the exercises. Some appear to be trivial. I won't do the easy one, but probably the next video will be with with something more with exercises that are not necessarily hard, but not trivial at least. So, see you in the next episode. Goodbye and ciao ciao.